I'm William Fortescue.
And I'm Leo Carlson. And our lab's question was, does a falling object's terminal velocity depend on its mass?
A more experimental way to phrase the question in the title slide is, what is the mathematical relationship between a falling object's velocity and its mass?
Our theory is that the terminal velocity is proportional to the mass. The terminal velocity is the speed that a falling object reaches when the resistance of the medium prevents it from further accelerating, and the mass is the amount of matter that a body contains.
The exact relationship of terminal velocity is that the terminal velocity equals the square root of 2 times the mass times the acceleration of gravity divided by the density times the projected area times the drag coefficient. The density, the drag coefficient, and the gravity are all constant values which we did not modify for this experiment. The mass is something we did modify, and as a result, the mass of the coffee filters changes the projected area.
For the experiment, we used different amounts of stacked coffee filters to ensure that the mass would change, so we could isolate the mass variable to see if the terminal velocity changed with it. Using the same materials also ensures that the density stays constant, and the projected area will also change proportionally to the mass as you increase or decrease the amount of stacked coffee filters.
Now, for our materials is, of course, the stack of coffee filters, which makes the whole experiment work. A balance for finding the mass of the different amounts of coffee filters. A meter stick, masking tape to secure the meter stick, a camera, and the one we used has slow motion capabilities, but you could just use a regular speed camera and get your data points from there. A black marker for the stack of coffee filters, a computer to export everything onto, and then a software on the computer called Tracker, video analysis and modeling tool, and finally the final point of all of the data, Google Sheets.
First, the mass of each stack of filters was found using a balance. Secondly, a meter stick was taped to the wall for calibration in the software program later on. Third, a camera was set up perpendicular to the drop. Fourth, vivid black dots were drawn on each stack so the auto tracker feature in the tracker software program could be able to track the filter stacks. Fifth, the filters were filmed in slow motion while being dropped. This was also to ensure that the tracker software program could be able to accurately track where these filters were in a certain given point in time or distance. Sixth, the videos of the drops were exported to a computer. Seventh, the tracker software was used to measure the velocity of each stack in every frame. We altered some of the parameters in the tracker program to ensure that we were getting the data points that were accurate to the lab. Eighth, velocity time graphs were created in Google Sheets, so the relationship between mass and terminal velocity could be easily seen.
The video on the screen right now is a documentation of the fifth step of our procedure, which is the actual dropping of the coffee filters. And we filmed it at this angle so that the tracker could see the dot when we were dropping it. And Leo also had to hold the filters a certain way so that the tracker would be able to see the dot once we exported the video. So now I'll play that. You can see that gets gradually faster once Leo drops it.
Since we filmed in slow motion, we needed to convert the tracker times into real-life times. We did this by dividing the times in tracker by 10 and subtracting it from the first frame to ensure that the first frame was the starting point at 0. In real life, the coffee filters actually move much faster than they appear in the slow motion video. So to convert the two times, you need to multiply the times recorded in slow motion by 10. The terminal velocity of the 27.07 gram stack of filters was approximately 5.1 meters per second, and the terminal velocity of the 6.02 gram stack of filters was approximately 2.3 meters per second.
Here is the velocity time graph of the 4 different amounts of coffee filter stacks. The blue corresponding to the largest stack, red to the second largest, orange to the third largest, and green to the smallest. You can see that both the green and the orange level out at terminal velocities. The green is a little harder to tell because of some technical difficulties, but the red and the blue are practically the same graph, and this is because neither of the 2 largest stacks of filters managed to reach terminal velocity during the drop.
The exact relationship is the terminal velocity is equal to the square root of 2 times the mass times the gravitational pull of the Earth divided by the density times the projected area times the coefficient of the drag. To make this mathematical relationship better applicable to our lab, we needed to change the formula to make it quadratic so that it fits our trend lines. So as you can see below, we listed all the equations in order to calculate the velocity at any given time.
Similarly to our initial theory, when the mass of the stack of filters being dropped decreased, the terminal velocity was reached earlier, meaning that the terminal velocity would be less in terms of magnitude. And as was seen in the graphs, the 2 heaviest stacks of filters were more or less identical graphs because neither of them reached terminal velocity. Our average R-squared value, and the R-squared value is a measure of how close the set of points are to the trend line, across all our graphs was 0.88, but the smallest stack of filters really dragged the R-squared value down, with it being less than 0.6, while all the other R-squared values were greater than 0.95.
Some sources of error that we came across while doing the lab were that the tracker software program kept losing track of the dot, especially on the smallest stack of coffee filters. And this was because the black dot was a lot harder to see and it blended in a lot easier with the shadow. We had to manually select points at a certain time to compensate for this. Another source of error that we ran into was that during the drop of the filters, they kept tilting vertically, especially with the smallest stack again. And so this made it harder for the tracker program to see the dot when the filters would tip in midair. And another source of error that may have been a problem was that we filmed in 1080p rather than 4K. This may have given us better data if we were able to film in 4K resolution. And the last source of error was not having a high enough drop for the first 2 filters to reach terminal velocity.
There are 2 ways that we think we can improve the experiment based on our experience in conducting it for the first time, and these ways are somewhat related to each other. And the first one is filming at 24 frames per second in 4K rather than filming at 240 frames per second with only 1080p, and filming at a lower resolution definitely limited the quality of our data. And also, especially with the smallest stack of filters, we should have made the dot on the coffee filters more bold, because when we dropped the smallest stack of filters, the software lost the dot multiple times.
Since we used a tracker program, we collected thousands of frames of data, and this was far too much data for it all to fit nicely on the presentation. But we do have a QR code that will take you to the spreadsheet containing all of the extra data.